spacing out here because I'm tired from yesterday. And so we still got to wrap up that 5 point something, 5.4. Where did I put my 5.4s? And I hope this hasn't been too tedious for you, because I just decided to kind of take it step by step on some of these. And get my black going here. So this is the 5.4 exercise. I won't write everything out. It's on page 4, right? Of the handout. So we got this 2 by 2 matrix A. 2, -1, 1, 3. And so we're thinking of the linear transformation that's just multiplication by A from R2 to R2. And I'm calling B this set of two vectors, 1, 1, and 3, 0. And that's a basis for R2. And R2, I've kind of picked an easy space for myself. It's two-dimensional, so any set of two linearly independent vectors is going to be a basis. And because it's two-dimensional, it's easy to tell if those two are linearly independent because they're not scalar multiples of each other, right? And so we're going to do this, find what's called the B matrix for the linear transformation. And two ways we're going to approach this. One is the slick way. We'll do that second. And you may already get the slick way. It's based on similarity of matrices. But so the first way, you might call the long way, is to just approach things very naively, like we don't know anything that fancy. I'm going to call these two vectors, let's bring a little color. So let's call them B1 and B2, our two basis vectors. And I want to write down what AB1 is. So 2, 1, -1, 3 times 1, 1 is 1, 4. And AB2 is 2, -1, 1, 3, 3, 0. And that turned out to be 6, 3. You can check. And see, the B matrix would be what you would multiply the B coordinates of a vector by to get the image vector's B coordinates. The B matrix would take you from B coordinates to B coordinates. So what we want to find out is, and I'll put question mark here, what are the B coordinates of those two vectors? And I just chose some variables to use here, x1, y1, x2, y2. So in the slick process, there's like just a fast way to pull this out, but I'm not going to do it the fast way. Okay. Why do I want to say this? Oh, okay. So I want to take this guy. Let's maybe bring in some more color. So let's take 1, 4. And if x1 and y1 are the b coordinates, that just means 1, 4 is expressed as x1 times 1, 1 plus y1 times 3, 0. Or turning that into a system of equations, that's 1 equals x1 plus 3, y1, 4 equals x1. Now, I gave myself a real easy system to work with here, but of course, it could be any 2 by 2 system. We could solve for x1 and y1. So I'm just thinking of this algebraically. x1 is 4, y1 is negative 1. And so that means the b coordinates of that 1, 4 vector are 4, negative 1. And we can do the same thing with the 6, 3. So 6, 3 has to be equal to, if I use this notation, x2 times the 1, 1 vector plus y2 times 3, 0. And that gives me a little system again. Of course, I can solve really quickly. And what do we got? We got x2 is 3, and y2, if I just plug in there, is going to be 1. So 3, 1 are the b coordinates of that image vector. Okay. So if we say so b1, which is 1, 1, what are the b coordinates of b1? As I dance around in circles here. It's just 1, 0. Right, because it's my first. Why? Because b1 is equal to 1 times b1 plus 0 times b2. Right. So the b coordinates of b1 are just 1, 0. I mean, these are coordinates designed for that basis. So those basis vectors are going to look like, kind of like standard vectors in their own coordinate system. And so under this transformation, 1, 0 in b coordinates corresponds to 4, negative 1 in b coordinates. b2, which is 3, 0. In b coordinates, that's 0, 1, because b2 is 0, b1 plus 1, b2. And we just notice that corresponds to 3, 1 in b coordinates. So in the land of b coordinates, this vector corresponds to that. This vector corresponds to that. So that means the B matrix is going to be 4, negative 1, 3, 1. It's just going to have these columns. Let's put some arrows on there. Okay, so, so that's one way to get the answer. And what is this thing? This isn't part of the work, but what we're saying is if you take the b coordinates of any vector, they're going to correspond under this linear transformation to the B matrix times those B coordinates. And this would give you the B coordinates of the image. So nowhere along the line here do we see our standard coordinates, like what we're used to looking at. Now, what's the short way? Short and fancy. And actually, that wasn't that long. It just, it was not that long because I gave myself an easy problem, but it's just sort of tedious working through those details. Call the B matrix of the linear transformation I'm going to call it C, okay, just because it matches some of the notation we've used. So I just pulled a letter out of the air to give it a name, okay. A is going to equal PC. P inverse to that matrix C. That's what we were talking about last time. And I want to add a little notation here. The P is going to be the change of basis matrix, or the B to standard change. And that means P inverse is the E to B coordinate change, right? So we take a vector here in E coordinates, put it on the right, multiply by P inverse changes to B coordinates, apply the transformation in B coordinates, and then change the B coordinates back to standard, and that really is what our original A matrix means. Now I can multiply on both sides here. I can multiply on the left by P inverse, on the right by P, and I'm going to get P inverse A. P is equal to C. Again, these, I like to put this on here. And let's see, the P inverse was the E to B change. Because if you think of C by itself, you start with B coordinates. What's C going to do? Change the B coordinates to E, multiply by the matrix A in standard coordinates, change the coordinates back to B. That's a way of thinking what C is, right? So those are, now what was our A? Our A was 2, 1, negative 1, 3. Our P matrix, somewhere in all our discussion, we actually have a rule for writing down what that is. The matrix that changes B coordinates to E coordinates is going to have B1 and B2 as columns. And just think about that. Just plug it in and see, and that'll remind you that that's what's happening. So P is just our 1, 1, 3, 0. Okay. And P inverse, you would have to calculate. So it is true, maybe that doesn't take that long to find the inverse of P, but I'm not going to go through those steps. Yeah? Oh, I guess it let's just say it doesn't matter which one we call P or Pn. We just have a matrix and its inverse. And I think we write I just wrote it this way because this is how we defined our similarity relationship. So I don't think there's any law that says, you could just as well call this one P and this one P inverse. The thing, it's not so much the P here is what changes B coordinates to E coordinates. I think that's the thing to know. So I don't, okay, so I'm not, it bothers me that you find that confusing, but I don't. So that's just this guy, right? And so again, there's no reason why we couldn't call this P inverse and this P, but then the thing is, you got to realize we're starting with this matrix. And it's not so much which one we call P and P inverse. You got to realize we're starting with the matrix whose columns are the B basis vectors is a matrix that's going to change B coordinates to standard coordinates. Okay. And that kind of makes sense, because if you multiply by a two-component vector, and I don't even want to put, I don't know what letters to use here that wouldn't be confusing, like Z1 and Z2 or something. You're going to take Z1 times B1 plus Z2 times B2. So those are exactly, these guys stand for the B coordinates, right? The weights of the B vectors that we would get. Okay, so calculate P inverse, and I'm just going to write this down. 0, a third, 1, negative a third. So you got to go through the process of calculating. And so if we write C as P inverse A P, this is my 0, 1/3, 1, negative a third. A, I'm just recopying, 2, 1, negative 1, 3. P is 1, 1, 3, 0. And again, it's not so much which one we call P, which one P inverse. I think the issue is this is the B to E standard basis matrix. This is the standard E matrix for the transformation. And this guy is going to take our E coordinates back to B. That's the thing you want to think about. And again, you can plug in a specific vector and watch what happens. When you multiply all this out, guess what we get? It's on the board somewhere. It's just this guy, okay? The 4, negative 1, 3, 1. So that's another way to obtain what we call the B matrix of the linear transformation. Is right here. So, I would have to think about that. Like, I wouldn't just. And yet, if you just work your way through those steps, there's nothing that profound. You just got to, once you see it, you'll convince yourself that this similarity relationship gives us exactly what we want. Now, I have a little bit more I wrote down here, so this is just sort of some extra thoughts. And I think this might help you guys too. I just picked 2, 5 in B coordinates, and what did I? Yeah, this is sort of picked at random. I just want to look at what happens to a particular vector here, okay? So 2, 5 in B coordinates, what is that vector? What is that vector is going to be the same thing as 1, 1, 3, 0, 2, 5, which is the same thing as 2 times 1, 1 plus 5 times 3, 0, where this is just B1 and B2, right? Get my colors mixed up here. And so what's this guy turns out to be is 17, 2. And that's just in standard coordinates. I mean, you could put a little curly e there, but we usually leave the e off. Right, because that's our favorite way of describing a vector with the standard basis. And all right, so what am I going to do now? I want to take that 2, 5 vector in B coordinates, and I want to multiply by the 4, negative 1, 3, 1. So the B basis vector, I'm sorry, the B basis matrix for the transformation. And again, that matrix takes me from B coordinates to B coordinates. So when I do what I got to do, what is it? That turns out to be 23, 3. Okay. And what are the standard coordinates? So the question is, standard coordinates? I can do the same thing I did up above. I can take 1, 1, 3, 0 times 23, 3. Or take 23 times 1, 1 plus 3 times 3, 0. I mean, that's what it means for these to be B coordinates. These are the weights of the B1 and B2 basis vectors. And I get 32, 23. That's it. That's the standard coordinate way of thinking of that vector. Again, this is all beyond the end of the problem. Okay, so I'm just sort of rambling on and on and on with my extra thoughts here. But here's the picture I want to give you guys. So remember, I picked this at random. I just picked one particular vector in B coordinates. We can now take our 2, 5 and B coordinates, apply the linear transformation. The linear transformation in this example. And what we figured out right here, we just mentioned, it's going to get assigned to 23, 3 in B coordinates, right? There's the linear transformation. Now this guy has standard basis coordinates, 17, 2. The same linear transformation is going to assign this 17,2 vector to 3223 in E coordinates, which are the E coordinates of that guy. So same linear transformation. You can think of it in B coordinates or in E coordinates. Almost done. So what process this is multiplication by, is that what I called C? Didn't we call that C along the way? Did I? Tell me if that doesn't match up with my C. I think that's multiplication by C, right? And this is the same linear transformation. This is multiplication by A. And so kind of my point is, if I were a student, it would really bother me that two different matrices define the same linear transformation somehow. Like they seem to be doing very different things. But this is the way we look at it. It's the same linear transformation. In one coordinate basis, C is the matrix you use. The same transformation in the standard basis is multiplication by A. And what we haven't done yet is, if I take 17,2 and multiply by A, I don't even remember what A was somewhere. What was A? A was 2, 1, negative 1, 3, right? 2, 1, negative 1, 3. Make sure I wrote that down right. That should give me this guy. And we haven't done that calculation on the board here, right? So I am purposely going around in circles. And what do I get? I get 34 minus 2 is 32. I get 17 plus 6, 23. Oh, doesn't that make you feel good? Did it all? No. So I hope you wrote this down, because I know if I were sitting there, I wouldn't just be saying, oh, yeah, I got it. I'm going to have to think about it a little bit. But it's not, the math isn't complicated, but it's confusing, these changes. And so this was just my attempt in these extra thoughts to, it's this, really this diagram that helps me understand what's going on. And remember, 2, 5 I picked at random. So I just picked a random vector, applied the transformation to it, converted to standard coordinates, applied the transformation to it. So it was all driven by that random choice of 2, 5. That's not part of the exercise. It just helps me to look at what happens to a very specific vector. So if you want, you don't have to shout it out now and embarrass me, but like, if this is like the most obvious thing in the world to you, and you feel like I'm just somebody come and tell me, because it's like, why does he keep? Because I felt like it wasn't obvious, and it was worth spending a little bit of time. All right, now we got one more exercise on that sheet, and it has to do with diagonalization. And really, the textbook focuses on diagonalization in this section. So this was sort of a journey and more abstraction. Even though it's a very specific, concrete example in R2, I thought it was worth thinking about that general situation. But if we get back to diagonalization, so this is the page 5 exercise. So we're talking about T is the transformation that takes a vector to A times the vector, right? And here what we want to do is find a basis for R2 with the property that, so this is the matrix of that transformation, in the basis B is diagonal. Sometimes you can do this, sometimes you can't. So the way we're going to do this is so we will find a diagonal matrix that is similar to A. And you know how to do it, right? I mean, that's what it means to diagonalize. What do we got to start out with? We need to find the eigenvalues. I think we went through this process. So start with A minus lambda I, which is 1 minus lambda 1, 6, 2 minus lambda. Now, this is not a hard calculation with 2 by 2. Imagine a 10 by 10 or 100 by 100 matrix where someone would be trying to diagonalize, right? Kind of an enormous computing challenge. And so the determinant of A minus lambda I is going to be 1 minus lambda, 2 minus lambda, minus 6, or 1 minus 3 lambda, right, plus lambda squared minus 6, lambda squared minus 3 lambda minus 5. So there's our characteristic polynomial. So we're going to set that equal to 0. And I think this guy factors, right? No, it doesn't factor. What did I write down incorrectly?
Should be a 2 minus 3
2 minus 3. Oh, you guys are so good. 2 minus 3 lambda plus lambda squared minus 6. And so I have lambda squared minus 3 lambda minus 4. Oh, I almost did it. I would have got partial credit. And so we got lambda minus 4. And it's written right here on my sheet. You know, if I would just look at my piece of paper. Lambda minus 4 times lambda plus 1. So lambda equals 4 and negative 1 are the eigenvalues. What's our diagonal matrix going to be? We already know what the diagonal matrix is going to be, right? We're going to use the eigenvalues in either order. There's no rule about which order. On the diagonal, zeros elsewhere. But now, those are not the basis vectors. The basis vectors are going to be the columns of either the P or the P inverse matrix, right, that we're trying to find. So we're not done yet. So for each eigenvalue, we got to describe the eigenspace, right? We got to find a basis vector. Find a basis for the eigenspace. A minus 4i is going to be negative 3, 1, 6, negative 2. So solve negative 3, 6, 1, negative 2, x equals 0, solve that homogeneous equation. We're looking for eigenvectors, right? And you're going to get, I'm just going to jump to the conclusion, x2 is free, and x is going to have the form x2 times 1/3 1. We got to do the same for the other eigenvalue. That was -1, all right? So we got to take a minus 1 I. So plug in the lambda value of it's actually going to be a plus 1 I, right? Minus a -1 I. And so we get 2, 1, 6, 3. And again, solve the homogeneous equation 2, 6, 1, 3, x equals 0. And that's easy. And you get, here again, you get x2 is free. So one free variable means a one-dimensional solution space here. x2 is free. The solution x is going to look like x2 times -1/2, 1. Now, you really can pick any non-zero scalar multiple of this vector, any non-zero scalar multiple of that vector, to use as your two basis vectors. All right, so you don't have to actually choose those two, but because they're vectors that correspond to distinct eigenvalues, they got to be linearly independent. Okay, here we're 2 by 2, and so we only have two vectors, and we see that they're not scalar multiples of each other. That's another reason. So my P matrix here is 1/3, 1, -1/2, 1. And my B basis is going to consist of those two columns. Oh, and I got to be careful here. I got to make sure my column 1, 3, 1 here, which correspond to lambda equals 4, so you got to make sure that matches my diagonal matrix, right? Matches the order of eigenvalues in D. So my two basis vectors are 1/3, 1, and -1/2, 1. No, I think I'm just going to stop. B basis means if we take the B coordinates of a vector times P, that will convert to E coordinates, and then we can apply the matrix A, right? And then I'm going to stop. All right, I did enough of this. So the answer here, by the way, is just, this is what we were trying to get. This basis that diagonalizes the matrix. Yes? No? Okay. Yes?
You could pick any scalar multiple of those vectors, 1/3 and 1, as an example, and -1/2 and 1.
Uh-huh.
So let's say you picked 1 and 3. Does that change your p basis? Your p and your p basis? It would just give you a.
Okay, I had more. I think this is just what you're asking, right? Let's just write this down. So I take b coordinates of a vector. So this is just 6 times 1/3 1 plus 8 times -1/2 1. So that's -2 14 in standard coordinates, right? Is this what you're getting at? And we can look at a specific example of how these matrices act. So under the linear transformation, this 6, 8 in b coordinates is going to correspond to something times 6, 8. Actually, that would be a good question for my test. Like, after we do all this, what goes in there? And we got all these. That's actually going to be the diagonal one, right? Right, that was the whole point. The b coordinates in this linear transformation have the 4, 0, 0, -1 matrix. I guess I'll give up on that blue. And that's going to give me 24, -8 in b coordinates. Now, 24, -8 in b coordinates is what? That's 24 times 1/3 1 minus 8 times -1/2 1. So these are just my basis vectors, right, from the two eigenspaces. And what did that come out to be? That comes out to be 12, 16 in standard coordinates. All right. So what we're saying is, okay, this guy's standard coordinates, this is really what we're used to thinking of as the vector -12, 14. And this is what we're used to thinking of as the vector 12, 16. And if all this is working, I should be able to take 12, 14 and multiply by the original matrix, the original A, which was 1, 6, 1, 2. And that better give me 12, 16, or I'm out of here. So -2 plus 14 is 12. Yes. -12 plus 28 sounds like 16 to me. Okay. So again, this is the linear transformation, which was originally just multiplication by the matrix A. This is the original A. This is the diagonalization of A. So it's that same diagram I drew a moment ago with a more general situation, but here it's just being applied to this diagonalization situation. All right, was that sort of your question? No?
Not exactly.
No.
My question was, I think I same question. Anyway, your P matrix, your P basis, you could change the P basis vectors by any
Right, so both the P and the P inverse would change, the diagonal matrix would not change. Okay, well, I should. Yes, yeah. Yes. Yeah, so there are really, for that P and P inverse business, there are infinitely many choices of P and infinitely many choices of P inverse, but they are paired. Once you choose a P, that sets the P inverse. So, I mean, should we say A, B basis is, right? So it isn't like there's just one choice. Yeah, that's a good point. I shouldn't use a definite article there. I wanted to start 6.1. That's why I was trying to finish, to just let this go. Because you're going to have to just think about it. And, but it's not hard. I don't think so. And I do think it was valuable just to, for me at least, I hope it was for you. Felix?
24 negative 8 and base B, right? By P, you'll get 12, 16, right?
It makes no sense to multiply this vector by A,
No, by P.
by a P.
And you will get 12, 16.
Should we, let's just write that down, right?
I'm just referring to the diagram.
Yeah.
So won't that be the change of coordinates from B to E, the P matrix?
Yeah, so changing from B to E, that should be what our change of coordinate matrix is, right? So if we take 24 negative 8 times P, 1/3, negative a half, 1, 1, there's our P matrix. Okay, we get 8 plus 4 is 12. We get 24 minus 8 is 16. This is B coordinates. This is E coordinates. This is a B2 E coordinate change. Again, so the magic isn't so much what you call P inverse. It's like this is the B to E change. Its inverse is the E to B change. And this arrow notation is just meant to help you see that the B vector goes on the right-hand side, and the E vector is, what you end up with after you do the multiplication. Okay?
Yeah, my question was because you have the equal sign, but that equal sign is, it's related to multiplying that by
Well,
P.
no, I mean, if we gave this a vector named V, that's V. That's the same vector. They are equal. Now, we're used to, like, if we're looking for the point in the xy plane, we're used to looking at it at 12, 16 in the xy plane. So this is that same point in the xy plane. Go back to that, was it the end of the previous chapter, where I had that graph grid where we looked at the same vector under different bases. This is, but these are the weights of the B basis vectors that will give you that point. So those are equal, absolutely equal. All right, sorry to keep you. And so we're a day off the schedule. We'll